about divide and conquer, right? Maybe. Okay. We talked about the basic idea, right? Basic idea is break up the problem into several parts, solve each part recursively, and then combine the solutions to those two problems into an overall solution. Most commonly, right, we break up the problem of size n into two equal parts of size half n, solve the two parts recursively, and then if we can combine the two solutions into an overall solution in linear time, and this is important, right, then we go from n squared to n log n, right? The book actually has a couple of has kind of the master theorem for formulas where you're not dividing into two and things like that. So there is more, but this is kind of the most common way, right? We talked about merge sort. Was I using these slides? Maybe, maybe not. I'm going to use these slides. Where the idea is to divide the array into two halves, recursively sort each half, and then merge those two halves to make a sorted whole, right? Merging is fairly easy to do efficiently. It takes order of n, except that it takes extra memory, right? So if you do merge sort, you go swapping your arrays over and over, right? On the other hand, merge sort is actually guaranteed n log n. Quick sort is not, right? Quick sort just usually works. This is what our recurrent relation looks like. We talked about all this, right? I'm going super fast, and you guys are not stopping me. So we talked about all this, right? And we are going to end up with order of n log n, right? We can think of it by the recursion tree. To me, this is the obvious way of looking at it, right? And understanding. We can use a technique called telescoping, which is, induction makes a lot of sense, right? And again, we talked about this case, right? In the case of merge sort, we have a ceiling on log n, right? Because we have here 1/2 will have, if the number of elements is odd, right, 1/2 will have one more. So that's why we are using ceiling and floor, right? We talked about counting inversions, right? If somebody has a rank, right? If you have two rankings, you want to try to count the number of things that are ranked differently, right? And so you want to find how similar are rankings. This is a measure of similarity, right? But you don't want to overcount those things, so you're just counting ones per thing that got ranked differently, right? Things that you ranked much higher or lower. Maybe you ranked this third and I ranked it fifth, but there is nothing in the middle, right? In the way that I ranked it. So you don't want to count those things double. So what we are counting is inversion. Some I and j are inverted if I is less than j, but ai greater than aj. So they are inverted in the ranking, and we'll only count it once per inversion. There is a ton of applications for this. Voting, collaborative filtering, measuring how sorted is an array, and that can tell us which algorithm do we want to use. A bunch of things like that. So, what's the algorithm? Divide, break the list into two pieces, conquer, recursively count inversions inside, right, each half. And then combine. We need to find the number of inversions between green in one side and blue on the other, right? Or blue-green inversions, right? Since we divided our thing into two halves. How can we make that fast, right? If we don't make it order of n, we are not going to get our beautiful n log n, right? So, in this case, it's just going to be whether the numbers are in different halves. And we can merge those halves. While we are merging, we count the number of inversions.
What is the 632200? I'm not following that. And you have it right below the green too. Sure.
This, right?
Yes.
This is because this 2 has 6, is before 6 of these numbers,
Okay.
right? This 11 is before 3 of these numbers.
Okay.
So that is the merging and counting. While you're merging, to keep track of how many you bypass. So what we are doing is very similar to a merge, but we are counting the number of inversions. So by doing that, we get n log n, which is really, really cool. We can, as another example, get the closest pair of points in a plane. This is important in a bunch of things, right? For things like geographic information systems, but also computer vision and a bunch of graph problems for geometry, right? For Voronoi diagrams and those kinds of things. How can we do that brute force, right? Well, just compare every pair, right? So we have n points, we get n squared-ish, right? Order of n squared is n times n minus 1, right? So it's slightly less than n squared, but it's n squared-ish, right? Can we do better, right? In one dimension, can we do better? If I give you a bunch of numbers, a bunch of ints, how can you find the two closest ones? Compare what?
Each one to its neighbor, because by sorting they're already close.
Exactly, right? So you compare with the neighbor. Does that make sense? How long does that algorithm take?
N squared log n?
How does, once it's sorted, how long does it take? Comparing each one with its neighbor.
So it take constant. Just 2, if you go all the way down to like 1.
1 per element, how many elements do I have?
N.
N, so it takes
N.
linear time,
Yeah.
right? Does that make sense? Once they are sorted, how long does it take me to sort?
And log in.
N log n. Which one is worse? Which one wins? I'm not multiplying.
Oh, you're adding.
I'm adding, right? So it's just which one is the biggest. So it's n log n. Does that idea make sense? Yes? Cool. To make our presentation cleaner, assume that no 2 points have the same x coordinate. What could we try to do? Well, I could try dividing my region into 4 quadrants, right? It doesn't really get me, doesn't guarantee a clean division, right? It sorta, kinda, I could hope, but it doesn't really guarantee a clean division. What can I do? Well, one thing that I can do is draw a vertical line so that roughly half the number of points are on each side. Find the closest pair in here and in here, right? And then find the closest pair that crosses the line, right? And then return the best of those three. Right? Our combining is going to be finding the closest one across the line, right? Does that make sense? How can I make this much more efficient? Right? Rather than just testing everyone in here with everyone in here, which would still give me order of n squared rather than linear. Do you see an easy way?
You sorted by x coordinate?
Well, it's sorted by x coordinate, but also, right, I can do this and say, oh, if you are more than 12 from here, I don't care about you, right? All of these guys, I don't care. You are too far away. You're never going to be the smallest one. Does that make sense? And that is what enables me to, so given that delta is the minimum of those two, I only need to consider these points, right? So I would sort those guys by their y coordinate, right? And I can almost merge these things instead of comparing everyone with everyone, right? 5, right? The only two that could be close, right, are 6 and 4. I don't need to test this guy. Right? Or do I? I only need to test if they are also within D, right? I may need to test more than 2. But I can also eliminate a ton of the other guys. Yeah. So if the y's are, right, I just need to check the points with the y's being close. Right? And this enables me to make it linear. If basically what we get here is 2 halves, and this stuff can be done in order of n log n, right? By sorting and sort of merging those two things. If I sort by y as I'm calculating this thing, then this sorting becomes just a very convoluted merge. And so I can do it in linear time. These are the horrible things that we should be implementing, but if we implement them, then yeah, that is the problem with this class. We either kill you or hand wave everything. I haven't found a better solution. Just for fun, as other examples, there is a cool series of algorithms about multiplication, right? If you're multiplying a complex number, right? You have a plus bi, c plus di, right? You end up doing it with 4 multiplications and 2 additions, right? There is a slight cheating way which allows us to do it with 3 multiplications and 5 additions. So if we are going by number of multiplications, I can do slightly better, right? Now, imagine that we are doing addition in integers, and we're going to see multiplication in integers. Given 2 n-bit integers, a and b, compute a plus b, right? How many bit operations do I need to do? This is the same thing as in decimal, right? If you're adding 2 numbers with 10 digits each, how many operations, how many additions do you need to do? 10-ish, right? So it's linear on the number of digits, right? Actually, yeah, it depends on where you count carrying, like a complicated addition, right? Same thing here, what's going to happen, right, is we are going to have order of n, right? For n digits, or bits in this case, right? Bit is just binary digit. So the grade school addition algorithm is optimal. For integer multiplication, right, the standard algorithm, right, would get us about n squared, right? If you remember, for each one of the digits on the bottom, we would be moving 1 space, right? And each one of those is an addition-ish, which takes us order of n, right? So overall, we get order of n squared. Does that make sense? Cool. Can we do better? Why are you laughing? Tell the
Booth's
joke.
algorithm?
Sorry?
Are we gonna do Booth's algorithm?
Maybe. This guy. Yeah. Yeah, probably. Maybe. No.
No?
I don't think it's called Booth.
That's what we learned in
Yeah, we're going
advanced
over
architecture.
exactly that.
in computer architecture?
Yeah.
Do you actually use? Nobody does that, right?
We need to know how to do it.
Yeah,
Oh.
I know. He was very adamant about booths is really important.
Oh. What happens in computer architecture? Is this important or not for computer architecture? No, why not? Why? It may not be booths. It may, like this stuff that we're doing, right? What do you do in computer architecture? The n is a constant factor. You know that you're doing 32 bits or 64 bits, right? And then you never do anything else. Does that make sense? So as far as we are concerned, who cares? That's a constant factor, right? We don't terribly care. This is more, what do you do if you had really, really, really long numbers, right? We can do the same kind of thing, right? Go by the first half and the second half of a number, right? And so we can compute a to be 2 to the n divided by 2 times a1 plus a0, right? So that's the first half plus the second half. Same for b, and then we can do this multiplication. Given that we can cheat, right? And by the way, this is shifting, right? This is just shifting. This is not really multiplying. That's bit shift, right? So we can do 4 recursive calls plus something or order of n, right? Which would still give us order of n squared. However, now we can cheat. And use something similar to the trick for complex number, which is Karatsuba's trick. That enables us to do it with 3 multiplications rather than 4. And so now we end up with basically 3 times, right? 3t of n divided by 2ish. And so by doing mathematical magic, they prove that this is order of n to the 1.585 instead of n to the 2. Don't think it's Booth's algorithm, but maybe. I have no clue. Does this matter?
Yes.
When? Does this matter for 64-bit ints?
No.
Why not? My n is tiny, right? I'll build it in hardware regardless, right? And that's what you guys are doing. When does it matter? When I have infinitely long integers. Do I do that normally? Not very much, right? So it could be, at what values of n's does this matter? Right? For normal people, no. When you're doing math, yes, right? Possibly. You can do something similar with integer divisions, and you can do something similar with matrix multiplication. If you remember your matrices, you can calculate the dot product of 2 vectors, right? It's just multiplying the first elements and the seconds and the thirds and add them all, right? So is order of n, where n is the size of your vector, right? You remember how to do matrix multiplication. You hated doing them, but you should remember how to do them, right? Basically, it is taking this and multiply it by this, right? We are cross multiplying, and that gives you one element, right? Or well, the other way around. This is this times this gives you this guy, right? And I may be confusing. Linda may keep me honest. Am I doing it the other way around? I can never remember whether it's this multiplied by this goes here, or whether it's this multiplied by this. One of them. First one is row multiplied by column. Cool. How long does it take? Multiplying two n by n matrices, right, takes you how long? Forever. What does forever mean? N cubed, right? You're doing n squared things, one for each place, and for each one of them, you take order of n, right? Because you're doing a dot product, right? So the total is n cubed, right? That's why it took forever. Yes, they took forever. How do you multiply matrices? In your programming class, you use a 3-nested for loops. Everywhere else, you get Octave or MATLAB or something like that and have them multiply the matrices. I didn't ever multiply matrices by hand. After you learn how to multiply matrices by hand. Now, can we do better? Right? We could by a similar trick, right? Here we are doing a small block, right? So, and by using a similar trick, we get, let's see, this is still, right? A11 times B11 plus A12 times B21, and then we add them, right? So we get two blocks that are half the size, right? So we are dividing our square by half, right? And then our addition is like this, right? Our addition is order of n squared. So we could partition A and B into half n by half n blocks, right? Multiply those things and then add them up. So that would get us 8 recursive calls on half, right? And so that's, and the addition is still order of n squared, so we are doomed. We still end up with order of n cubed. However, we can cheat and get 7 multiplications instead of 8, right? By doing all sorts of horrible math. And by doing that, I get order of 2.81, order of log base 2 of 7, right? Rather than n cubed. So it's n to the 2.8. Is that much better than n cubed?
Again, if it's a larger
Better.
value.
It's better, right? Do you use large matrices? All the effing time. Maybe. At least theoretically, you tend to use, right, huge matrices when you do any kinds of data mining or data algorithms, right? You are conceptually doing huge matrices. Is this worth it? Yeah. for some values of n, right? Now, in practice, is that good? Well, maybe. This is Strasson's algorithm. There's a ton of implementation issues. How sparse is your matrix, right? Many times when we do, especially these kinds of image processing or data mining algorithms or something, data mining, those kinds of things, we have very sparse matrices, right? There's mostly zeros. Depending, it may be more for many not so big values of n, caching, right? Having this stuff in cache, for those of you who are studying computer architecture, makes this stuff much faster, right? And so if you can have locality of reference, then that can help, right? There is all sorts of stuff with numerical stability. You are doing multiplications with floating point things, and floating points arithmetic is weird as hell. Nothing works, right? And so, depending on what you do, you may get more errors or less. If the matrices are not even or not, right, being able to divide by 2, your algorithm becomes more complicated. This will vary a lot, but around n equals 128, then Strasson's algorithm would work, right? Well, right? It depends. There is one paper that they cite, right, with n of 2500, you get an 8 times speed up, which is actually, right, reasonably useful. When do you use one versus the other becomes a lot more painful than you would imagine. It's really not just a matter of algorithms, right? And you can do a bunch of other things with a similar thing. Eventually, with really large matrices, you want to do that, but what's really large and those kinds of things are matters for investigation. What's it here? In the book, they report that Octave or one of those, everybody uses BLAST for matrix multiplication, a library. That thing has 5 different algorithms depending on a bunch of different things. They use one or the other. So, and so there is some other things for what can you actually do with matrix multiplication. That's not terribly important. The best algorithm actually has n to 2.37.
What does best mean?
The best known at the best n, and the best power of n, the lowest power of n. So almost n to the 2.4, which is good. There is a conjecture that you can do it arbitrarily close to n squared, but by having horribler and horrible constants. So any of those things, right, end up being not terribly practical. Even Strasson's is not terribly practical. And this is on matrix multiplication. The one for integers is basically, I guess somebody uses it, but it's not very commonly used. the really cool thing, right, is that what we are doing is breaking our problem, right, into smaller problems, right, and then combining. It's the exact same idea. And so in many cases, right, you can, when given a new problem, say, can I break it apart and then combine, right? Would that get me, and that maybe may move the order of magnitude, the time that an algorithm takes. Let me cover this, but don't worry, I promise you I will not ask you about fast Fourier transforms. There is, if you remember your calculus, you don't. Okay. Basically, Fourier's theorem and a bunch of other guys, Riemann and those guys, basically say you can approximate any function, right? There is function theory, right? You can approximate any function by adding a bunch of other functions. In particular, you can approximate any function, right, as the sum of a series of sinus functions, right? You know, the sinus function is a wave, right? Goes up and down, up and down, up and down. And so you can, by multiplying, you get higher peaks and valleys, and by multiplying inside the sign, you get wider peaks and valleys. And so you can approximate any function by a series of those. Also by Euler's identity, right? Your sinus functions are a sum of sine and cosine, because e to the ix equals cosines of x plus I sine of x. So you can think of your sines as sum of complex exponentials. This is where, if you're an EE, you get a piece of magic that normal people don't. You can transform stuff from the time domain to the frequency domain. And the standard example is a sound wave, right? You can think of a membrane that moves, right? And that's what sound is. Why is that? Why is sound a membrane that moves? Because that's actually what you have in your ear. You have a membrane that moves, right? And that's what we're representing, right? And so you could think of, you put a dot in the middle of that membrane and record its movement on the x and y, right? And that tells you all you need to know about the sign, right? So that is, over time, what is this y? If your time is x, what is y, right? Now, the Fourier transform allows us to map from that time domain into the frequency domain. So rather than think of it as it is this horrible function, I could, if I find the right thing, right? Oh, this is just the sum of these two sine waves, right? So in terms of frequency, this is the sum of this one plus this one, right? And on the frequency domain, my sine waves are just frequencies, right? Each frequency represents one sine wave. This enables me to do all sorts of magic with sound, right? It enables me to do all sorts of magic with all sorts of signals that may not be sound. right? To tell you the truth, I don't have this magic. I understand the concept. I don't have it, right? I'm not an EE. If you study electrical engineering and those kinds of things, you get to the point where this magic becomes obvious. And we can basically approximate, right? Chances are that if you get a real sound wave, it doesn't look exactly like this, but it may look like this. And so you can say, well, you know what? I can kind of forget about this stuff, right? Just take this one and this one, and I have a lot less information. The fast Fourier transform allow us to go between time domain and frequency domain in a much faster way than before. And it was amazing, well, partly because of computers, but partly because we got the fast Fourier transform that we do all those sorts of things, right? You know auto-tune, right? Where they can make even me sing beautifully. It's this stuff, right? Just map it to that frequency and that's it, right? All those beautiful things that you can do with Audacity and waveform and those things are basically just this. An alternative viewpoint is to view it as a fast way to multiply and evaluate polynomials. And this is everywhere, right? Because also images can be considered as light, and so you can actually transform them and apply them to images too. So this is used all over. It is not matrices, but it's close. It is one of those things that I regret that I have never really grokked. But one of these years, when I retire, the fast Fourier transform wasn't, of course, considered terribly important until we have computers, and now we can do it, right? You also needed the constant factor that computers give you. They are a couple, right? They're a few million times faster than humans. One way to think about it is having polynomials, right? Polynomial is a0 plus a1x plus a2x squared plus all the way to a to the n minus 1 x to the n minus 1. How can I represent this in a computer? I don't need to represent the 1, 2, n, so it's just a vector of coefficients. Does that make sense? I just need to store a0, a1, a2, and so on. Does that idea make sense? Yes. Cool. Adding is order of n. I just add up all the coefficients, right? In a way, this is the exact same thing as the standard algorithm for addition, right? To evaluate this thing takes me order of n. You can use Horner's method or just keep track of the x's, right? Horner's method is prettier. And that is just start with the x to the n minus 1 and keep multiplying by x and adding the next coefficient all the way to a to the 0, which doesn't get multiplied by x. You normally implement it that way, but going the other way. Right? Just keep track of the current x to the n. Now, we can multiply or convolve two polynomials by an order of squared thing, right? We are basically, we need to multiply each coefficient on 1 times n and keep adding, right? So it's n squared-ish. Does that idea make sense? There is another thing proved in this thing, Gauss's PhD thesis, right? Gauss is one of those guys who is a genius and was, for some reason, we all decided that he was a genius, and so now we say all cool things about that he did, right? So that's his PhD thesis, right? Basically, a degree n polynomial with complex coefficients has exactly n complex roots, right? You remember that stuff. Root is x equals 0, or actually y equals 0, right? And so a polynomial of degree n has n-ish roots. So degree n minus 1 polynomial has n roots, and so you can just specify those roots. Actually, you can specify its evaluation at any n distinct values of x, and then you can approximate with degree n minus 1 polynomial. So another way that I could represent it, right, is by keeping n numbers, right? I can add in order of n. I just add up the numbers. As long as we are using the same x's, right? The same values of x. Multiplication is order of n, but I'm going to need more points. And evaluating using this horrible formula, it will take me order of n squared. However, if I can move, right? So basically, what happens is, if I represent it with coefficients, multiplication is order of n squared, but evaluation is order of n. If I represent it with points, multiplication is order of n, but evaluation is order of n squared. If I have an easy way to go from one to the other, then I can make both of them fast. Right? If I have a way of transforming from one to the other. And in a way, that is what the fast Fourier transform gives us. How can I brute force it, right? From coefficient to point value, I just evaluate at n distinct points. Evaluating takes order of n. So overall, I end up order of n squared. I didn't gain much, right? It doesn't give me anything. From point value to coefficient is actually worse, order of n cubed, or I can do slightly better if I do fast matrix multiplications. I can do divide and conquer. In frequency, I can break up into low and high powers, low and high frequencies. Over time, I can do even and odd, right? And then keep going this way. The idea is that to go to a coefficient to a point, I can, given a polynomial, evaluate it at those distinct points. My divide could be break the polynomial into even and odd powers. And that basically gives me right? Get half of the coefficients. And given that if I try to get evaluate at x and evaluate at minus x, right, I can obtain those two by only evaluating three polynomials. Actually, only evaluating two polynomials, this guy and this guy. And then my even powers are not going to change if I do minus x, but my odd powers are going to be, right? So I can just evaluate two polynomials of degree half n at one point, and I get two with complex numbers. It is similar. I can evaluate a polynomial of degree n at 4 points by evaluating two polynomials of degree half n at 2 points. So that is amazingly cool, right? What could I do? Well, here's where it starts getting even hairier. I have to choose those WKs where the W is the, or omega. Omega is the principal nth root of unity. It is similar to the root, but except that get me 0 gets me 1, right? And nth root of unity is a complex number x such that x to the n equals 1. So the fast Fourier transform basically involves getting those roots of unity, calculating this for even and odd. I just need to calculate this once, either add or subtract, and that gives me 2 points. And the running time is n log n. For the inverse, given the points, find the polynomials. And we can do it with basically the same algorithm, but using this. And so I can go from one to the other in order of n log n. Which means that I can now do either one of these, right? Faster. Everybody uses the fast Fourier transform everywhere. On the other hand, this is the realm of the EE people, and so we tend to not learn it too much. When I'm 65, Georgia will give me free tuition, and I'll come and learn EE stuff. One of these years, I'll take a graduate class in this stuff and one in control theory. That other stuff is also really cool magic that I don't know. We saw, right, integer multiplication, right? we can get it, we can get integer multiplication as, and do kind of like a fast Fourier transform on it or something like that. So we can get slightly better than what we had. Order of n log n log log n operations. Our lower bound is always going to be omega of n, right? And maybe people will be coming up with new algorithms to get it slightly closer to omega of n. Given an n-bit integer, find its prime factorization. What do I need to do? What's the easiest way to do it? Start with 2 and start checking whether they're factors or not, right? Once you do it, then you go low and keep going. One of the encryption algorithms that we used is RSA, and the idea was there's a private key and a public key, and they're basically two really long numbers, right? And in order to encrypt, you multiply by one, and in order to decrypt, you multiply by the other, and then use the total thing. So you could encrypt with 1 by multiplying with 1. I can just multiply by the other and get the same thing. And I could also multiply by 1 and encrypt with my private key, and you would know that I have that I encrypted it by multiplying by the other guy, right? And so it involves two huge numbers. It involves a prime, an almost prime number, two large prime numbers, or prime-ish numbers. The more factors they have, they don't need to be perfectly prime, but the more factors they have, the less useful this would be, right? And so if we can find efficient primality testing or efficient factoring, right, we can break RSA. And there is a polynomial time algorithm for primality testing. Just to mention this stuff, you don't need to know. We're not really going to talk about quantum computers. But this is all the Shor's algorithm can factor an n-bit integer in order of n cubed time on a quantum computer. So if we ever implement quantum computers, we broke encryption. We broke RSA, which is in SSH and all of those things, right? So at least one of the following is wrong. Either RSA is secure or textbook quantum mechanics, right? Or the Church-Turing thesis. I'm putting my money on this one. But is it terrible right now? Meh. Equifax just released all your information, so who cares about Equifax just released it in plain text, so yeah, just know that this thing exists. You have an assignment due Wednesday, and I will come with a sample test. I need to create a way of doing a test. We'll come up with a sample test and then we'll have the actual test on Monday. Right? The 25th. Cool. I'll see you guys eventually.